A robot wants to pick up an object which it is obstructed by other objects.
Which objects must be moved out of the way and how?
Symbolic and geometric reasoning are not independent. Decomposition may cause lots of backtracking.
We integrate task and motion planning by using a task planner capable of geometrical reasoning. Our task planner handles both functional strips and also state constraints.
The state constraints express that no two objects can overlap in the space.
Our algorithms are very efficient for many experiments and realistic problems with 3D environments.
Our integration of task and motion planning is fundamentally profiting from task planning in an expressive language.
Namely, we added state constraints to functional strips.
We now see an example where the mission requires planning combinations that involve the moving of the entire robot, the robot's arm, as well as the planning of tasks and actions.
The assembly of a pile of blocks is a classical example of the reasoning behind task planning.
But moving around the table and avoiding collisions is also an illustration of motion planning.
More interesting is that disassembling the pile is not equivalent to all actions in reverse.
The capacity to combine task planning and motion planning allows challenging structural settings to be sorted, like placing the wood on the two cubes. Runtime verification on two robotic learning tasks.
This video illustrates runtime verification over a robot that is performing two simultaneous learning tasks. We use logic-labeled finite state machines to represent all behaviors. Formal model checking is infeasible as the software is changing as it's running.
The first behavior is learning the environment and its obstacles in the same style as the seminal robot for behavior-based control named Toto.
The robot wanders avoiding obstacles, and with its exploration, it builds a topological map. The map enables BEAR to gain constants for its feedback loop control, and to, later on, use task planning for more efficient mobility.
The second behavior is also performing a learning aiming at controlling the arm.
Because the weight of different parts causes challenges, for example raising the arm by a particular angle requires more power than lowering the arm by the same angle.
Each learner is working independently and concurrently.
But the movement of the robot may cause the arm to reach dangerous configurations.
We use a novel software architecture to provide runtime verification against dangerous positions of the arm while moving.
The architecture is inspired by the subsumption architecture.
However, lower layers are not considered complete or correct.
The monitor behavior and the subsumption switch are also logic-labeled finite state machines.
But the behaviors of the original system can be suspended and new behaviors dynamically loaded by the monitor on the fly. When the monitoring behavior detects a dangerous configuration of the robot's arm relative to its movement, it suspends both learning behaviors. Scoping the traveling with a higher priority command to the switch, it suspends the arm learning routine and dynamically loads a folding arm behavior that brings the arm to a safe position.
Once the arm is in a safe position, the monitor unloads the folding arm behavior and resumes both learners.
Although we have a complex system of two learners with an enormous amount of configurations, the monitor and the switch are both small enough logic-labeled finite state machines that can be formally verified.
Similarly, the folding arm behavior is sufficiently simple to be subject to model checking. The system is efficient because the entire system is configured of compiled finite state machines.
Our architecture enables to launch a robotic learning system that verifies itself as it executes.